All right, so we had a bit of a break. We're going to try to get back to things. We started with rings, subrings, ideals, and today we're going to do a short review and then try to get to the first isomorphism theorem for rings. We're not going to do a proof because I think that it's very similar to what we already did, but I will give you like just an outline of a proof, like what needs to be done, and then we'll give it as a home exercise. Okay, and I think that that may force you to go back to what we did with groups, and then it'll make sense. Okay, so today is really, it's nearly just a review. Okay, and actually what we're preparing for is that next session we'll be going into finite fields and also polynomial rings. Okay, that's okay. So let's just quickly go through. So we spoke about rings. Okay, we said that rings are defined. They're actually a set with two operations, right? Plus and multiply. Okay, and then what we're requiring is that the plus. I'm writing a little shorthand. Okay, is abelian. Okay, and you should already know what that means. We want that the multiplication, I'll just mark it like that because maybe it's easier to see, is closed and associative. Okay. And we would like the distribution, right, which basically means that's the property that we have on both the addition and the multiplication. Okay. And then we saw that actually the properties, maybe nice properties that we want or in this structure that make it a little bit nicer, that we're missing, right? So what are we missing here with multiplication? So we're missing a lot of things, right? We're missing like a multiplicative identity. I mean, not necessarily, but like in the maybe like most general form, right? A ring doesn't need a multiplicative identity. Right, it doesn't need an inverse, right? Right, and it also doesn't need to be commutative. Maybe that's right. We'll just do and then we saw that we defined special rings, right? So we had like ring with identity, commutative ring, and then we had this special kind of ring that that we called an integral domain. And actually, the integral domain had an identity. It was commutative, but it didn't exactly have an inverse, right? Instead, we actually said that so this is like we exchanged it for an inverse. It's not equivalent, right? But we said instead we'll do no zero dividers. Right, which means that if any product that equals 0 has to have that one of the arguments is 0, right? That's no zero dividers, and that already gives us quite a lot of structure. Okay, so that's just really going back, and then we continued to subrings. Okay, so maybe I'll just erase this. We'll reuse the top. So if we now go to subrings, it's become pretty noisy. So subrings, they're a subset. It's a subset of a ring. All right, subset of the elements of the ring. What else does it need to do? It needs to be in itself a ring with regards to the same, right? The same operations as what we had in the ring. Okay, so we can't have like different operations, right? And it actually, I'll just phrase it because we talked about it in more detail, last session, but it needs to actually, I'll say it loosely, okay? I'll say have same structure as, I don't know what to call it, mother ring, okay? What does that mean? So, for example, if the ring had an identity, right? So the subring has to have the same identity. It can't have another identity, right? If it's a ring with identity, it's got a subring. The subring has to have the same identity as the ring. Otherwise, it's not a subring of a ring with identity. Okay, so then we continue to special forms of subrings that are of interest to us. Okay, and again, each time we add properties, we essentially restrict the structure more, so it gives it more structure. Okay, if you understand what I mean. Okay, so special subrings, right, are ideals. Now an ideal, right, what we defined is that that for each A in J, okay, J is an ideal, okay, and R in a ring, okay, and we say that J is an ideal of that, okay. Then this means that AI, the multiplication of A and R, has to be in the ideal. Okay, that's what we define. So, in a sense, this replaces the closure that we had, and it's a stricter closure. Okay, because if previously we had to just have the closure within the subring, okay, now we need to have closure within the subring, but also for multiplication from outside the subring. That has to map to inside the ideal. Okay, now we spoke about this. This would essentially, if we define it like this, right, then this would be what's called the right ideal, because we're multiplying from the right. But like we said last week, we are always going to assume that we're in a commutative ideal or ring, and so the ideal is two-sided. Okay, and we need this. We will need to have this property that the ideal is two-sided and not one-sided with what we want to do with it. Primarily, we'll soon see when we get to what's called quotient rings. And it's very similar, if you remember, with groups, we wanted normal subgroups, right? And normal subgroups were also they're essentially two-sided subgroups, right? That the right cosets and the left cosets are equal. And I think that we didn't actually dive into that nuance. It's worth just for you guys to just, find that there are various videos where you can see why you actually, in order to, like for groups, in order to create a quotient group, you actually need, you need to divide it by, or, like take the remainder of it with a normal subgroup and not just any subgroup, okay? And here it will be the same. Okay, now, I don't know if we did this, but there's what's called the principal ideal, okay? Now, principal ideal, it's just like a normal ideal, but it can be generated from one element, okay? And we actually usually mark it like that, okay? And then we say that this is equal AI such that R is in I, right? And if you look at this, right, so it's actually, right, A would be the generator of the principal ideal. And you actually take all multiplications of A by elements of R, and if you think back to groups, it's somewhat similar to cyclic groups that we define. Not exactly the same, because with cyclic groups we actually look at integer multiples of A, and here it's essentially not integer multiples of A. What we will eventually deal with, because we're going to finite fields, it will be the same. Okay, so we're not going to deal with these nuances, and they can be very complicated in structure, but note the similarities. So when we talk about a principal ideal, it's got similarity to, at least in certain situations when, say, R is Z, for example, to the cyclic subgroup, okay? And we'll make a lot of use of that. Now, we mentioned briefly where this whole ideal thing came from. So I'm going to talk about it just on, it's not so relevant for what we need to keep going, but I think it's worth mentioning, okay? And again, without proof, if you want, you can look into it. I did think to show you the proof, and it's not overly complicated, but what I'll show now without proof. But I just don't think that it really doesn't matter much for for the path that we want to cover. So I'm going to skip it. Excuse me. Okay. So when we talk about principal ideals, we can talk about a principal ideal domain. Principal ideal domain. Okay. This is also a type of ring. Okay. Now, principal ideal domain is actually an integral domain. So we inherit the structure, and by the way, it's often called PID. Okay. So we inherit the structure of an integral domain, But additionally, in a principal ideal domain, every ideal is principal. Okay. And you could sort of think why this creates some structure. If I can generate every ideal from one element, okay, you can think of it in a sense gives it some sort of like nesting structure, okay? And that's part of the proof of what I want to show you. When I say nesting structure, I mean that the ideals are nested one in the other. Okay? And then you've got this one ideal that is actually right, because we always have the we spoke about like the trivial ideals, right? Are always 0 and then R, right? They're ideals. So what we have in a principal ideal domain is that like the biggest ideal is generated by one element, and then all the other ideals are in a sense nested in it. So you have this like like a I don't know how to call it, like a nested structure.
Can I give an example for this?
So yeah, I mean you can take like Z is like a principal, the ideal domain. Okay, right, and you can see that that like if you take right, like any number, like it would jump just in multiples of itself, and it will be nested at least in some other one, and then the big one would be 1, right? Because that will generate everything, right? Yeah.
Is there any definition for the ideals which are sort of factor belonging in mutually exclusive except the common trivial point?
So I think we spoke about it last time. Yeah, I prefer not to go back there because it's not really on.
Okay.
But go back to the previous session, and we spoke about you know like right, multiplications of ideals and additions and unions and intersections and what happens.
But it's not a principal ideal. Like the principal ideal is not encompassed.
It's not a. You can have. I think that you can have like a ring that has principal ideals. I mean, right. And it would have other ideals as well, right? So you would have a mix.
Yeah.
But a principal ideal domain, because it forces everything to be principal, it creates a certain very regular structure. Now, there is something called, so if we go from, there's actually like also this like inheritance type of structure, okay? Of all these different domain structures, right? Like we're saying like principal ideal domain is always an integral domain, okay? So integral domain, in a sense, contains all the principal ideal domains, but it contains other domains. So in the middle between these two, there's another type of structure called a UFD, unique factorization domain. And here you'll excuse me, but I'm really only going to briefly describe it. And what I want to say, I'll describe it in a sec, but what we're going to say is that every PID is a UFD, okay? And UFD actually, it actually has this property that is similar to what's called the fundamental theorem of arithmetics. Fundamental theorem of arithmetics, I'll just say it without writing it, but it basically is like a prime factorization theorem, okay? Like any number that is not prime can be defined as like uniquely as a multiplication of primes up to order, right? So unique factorization domain is actually a more generalized form of it, okay? And actually, it could get a little bit ugly and complicated, so we're not going to go into the details, but we are going to say that it is an integral domain, okay? It's a more general structure than PID. So PID is a type of UFD. And we're going to say that every non-zero, non-unit, and I'll say something about what a unit is in a sec. Can be is written as a product of irreducibles, which I'll also say something about in a sec. Again, uniquely up to the order. Up to order, okay? Now, okay, so non-zero is easy, okay? And sometimes the zero is included because actually zero is not so interesting, basically. A unit is, it's very confusing, but a unit is actually an element that is invertible, okay, that has got an inverse. You need to see that because we're actually looking at a very, a much less structured thing than I guess what we're used to with fields, right? Because field is say like by far more restricted than even PID. So we actually divide the elements into zeros, units, which are invertible invertible elements that have an inverse. What?
With respect to multiplication.
Yeah. And yeah, because addition is easy. It's always abelian. We've got everything we need, right? And then all the other numbers are called non-units. And when we talk about irreducibles, when we talk about a product, we actually are looking for a product of like a non-unit to, like I want to define it as a product of two other non-units. And I want to define it with irreducible non-units, meaning that those non-units cannot be defined as a product of something else. They're basically like the end of the road. Now, these are not prime numbers, okay, because the definition of prime is actually different. And I'm not going to touch on that nuance, and that really has like, it's quite complicated to see like the difference, and a lot of times they're the same, and usually in areas that we care about, the irreducibles are also prime. But specifically here, it would not be correct to define this as prime. And of course, these non-units, right? You could always what happens with units is that you can always multiply them by units and they stay the same. Okay, so you don't care about multiplying them by units. Again, when you present it as a product of non-units, because it's an integral domain, you've got the commutation. You can actually exchange the order. It doesn't make a difference. Okay, and what essentially I wanted to say is that principal ideal domains are always UFDs. Okay, so that nesting structure in a way gives it this property, and that's it. And we're not going to, if you're interested, you can dig into PIDs. For the moment, we don't have that much use for them. We're going to go back and concentrate on ideas.
This will be important to understand, for example, how later on when you want to understand this elliptic curve group factorization.
It may be, yeah. So we're going to actually, I think now, go to finite fields. And I think, if we decide to, after we do finite fields, to continue to elliptic curve, we may want to revisit this stuff. Yes, for sure. Yeah, and that's why I'm mentioning it. But we're not going to dive deep into it. I mean, there's infinite complexity if you want to go, down into these structures. I'm not sure that I'm the person to actually explain about it. Okay. So let's continue. So we're going back to ideals. Okay. We're going to talk about ideals, but all the examples will be with principal ideals because it's easier. Okay, so if we have a J, right, that is an ideal, right, and we is this the way that we right? That we defined ideals.
It's like a subset. You want it to be a subset of.
No, it's not a subset. It doesn't matter. Let's just write it in words. No, I think that this is the way to.
But what if J less than R?
Yeah, so it's not less than. You can do it as a triangle. Whatever. J is an ideal of R. Okay. So if J is an ideal of R, so J actually defines a partition. Okay. J defines a partition of R, okay, into, we don't, since it's partition, it's disjoint, but we'll say it explicitly, disjoint cosets. Okay, and we do this, okay, specifically, we do this with regards to the plus operator. Okay, very, very similar to how we used right the subgroup to define a partition on the group. Right, remember with the equivalence relation, we can also show how to get the ideal. We can use an equivalence relation, but it doesn't matter. Now, the nice thing is that if we define a partition of R using J and addition, then what we get is the following. So this, right, and we'll just already call it this partition, which is marked like this, right? It's actually is a ring. okay? But it's a ring with the following operations, okay? We need to define plus, like addition and multiplication, and again, they're not going to be the addition and multiplication of R. Okay, they're going to be something different, okay? How are they defined? And this should, in a sense, be like a review, right? Right, so if we have A plus J, right, this would be an element, one of the cosets of the partition, okay? And we add it to B plus J, which is another coset. Right? What we would get is A plus B. This is the normal. This is the special addition. This is the normal addition. Okay. Plus J. Okay. And this plus is whatever. This is in a sense it's a little bit like the normal addition. It's just what forms the coset. Okay. Because this is a coset with an element.
Can you mark them differently?
Yeah,
Special.
maybe put
Mark it with a circle on the plus.
a plus tilde or
Fine,
whatever.
fine. Like this.
And then it means
This is
it's
okay.
okay.
This is the special.
This is the special addition, yeah, because we're adding cosets, right?
Right.
When you add an element to a coset, you can sort of understand, right? You add like one element to all the elements of the coset.
Right.
It's in a sense very similar to the normal addition. But what happens when you add a set to a set? What do you get?
Yeah.
Okay? Does the order matter? Do you add like the first element to the first element, second to the second? Like, what's the?
And the
Is it a
plus-
set? That's this plus.
And the plus on the right hand side of the
This
equation,
one?
Yeah.
You tell me. What is this plus?
I think you should just mark it with a circle, right?
Why?
No.
Okay, let's see. The internal plus here is just two elements, right? So this could be element C, right? What's this one? What am I adding? I'm adding an element with a set, right? So that's just like here, right? No?
This means add this element to all the items in the set in the regular like.
Yeah.
Okay.
Yeah. It's basically, it just means like take the set and offset it. Right?
Yeah,
Like,
okay.
like it's like a
Yes.
like in geometry it would be called like a translation, right? That's all it is.
Okay.
Right? I don't know if that's the right terminology, but I think it is.
It's like the combination of translations is the no. Yeah, but like this is not
Okay.
offset, and then you combine.
It's
All right.
just that this joint concept that you get
Right.
from adding A to all of the elements of
Mhm.
the idea.
Yeah. So you can say that it's pretty much the same addition, right? But this is definitely not. Like this has to be defined. This is why we define it, right? Multiplication is the same, right? I mean the same as in it would be that. And you can probably guess that we're already going to end up with this, right? And you know what? Just for your convenience, even though I'm not such a fan of these max because these have like different meanings a lot of times. But just for this presentation, okay? So the special multiplication, again, you multiply the elements and you add and you offset the idea. Okay, now things to notice. So obviously, like, and I think we already looked at this, everything to do with you know, with addition, with the abelian group, right? So it gets preserved in a way, okay? So like if I want to talk about what is the identity of, like what is the additive identity, right? If say the additive identity in R is 0, what's the additive identity here, what is it?
0 plus j.
Exactly, 0 plus j. Right, so, and we would, by the way, maybe I'll do it in a different marker just to, right, so we would mark it like this, and this is what we did with groups as well, right, is 0 plus j, okay, or just j. And the identity for multiplication, we'll just use 1, okay, we can mark it something else, but just imagine that 1 is not necessarily the number 1, it's the identity for multiplication, right, would be 1 plus j. Because if you do that, then if you go back to here and you see that, like, if you take this and multiply it by something, it stays itself, so it's the identity.
Yeah.
Okay? And we have an identity, right? Because it's an ideal, right? And actually, yeah, well, not necessarily, but if we do have an identity for multiplication, this would be it, okay? Because at this point, I think that R, we haven't really forced R to be an integral domain. All right, so by the way, this is called, so this thing, right, it's got a few names. I like the name quotient ring, okay, because it's, we have quotient group, now we call it quotient ring, but there are other names that you should know. There's also factor ring. They're all interchangeable. There is, these are called, you remember we had a name, we called these equivalence classes in groups. Here they're called residue classes. So this is often called the residue class ring. Okay, so it's got various names. They're all the same. Okay. Let's take an example, okay, of a partition. Our examples are going to always be simple. Here as well. Okay, so it's a very simple example. Ring. Okay. So take Z and over N is now just a principal ideal, okay? Which is basically all the multiplication, all the products of N with Z, but it's right. It's very similar if you remember we had the cyclic group N, right? It's actually the same elements, right?
This is the product.
What's a product?
The bracket and
So this is all the products of N with Z?
Yeah, N is defined as AN such that A is in Z. It's exactly the same as, again, you can have more complicated like ideals here, but I'm just giving the simple examples.
is
Huh?
for all A and Z.
Yeah, this is for all A's and Z. Right. So it basically just be all the integer products You understand how this looks, right?
Yeah.
It's just like, it's sort of like a
Like
one-dimensional lattice
Yeah.
on the integers. Okay. Well, so, I could have left it. Anyway, we know that like, what are the elements of this? It would be 0 and 1, okay, and everything up to n minus 1, okay? And each element here would be, like, if I take, like, what is A? It's A plus n. We see that it's just like an offset or a translation of the basic ideal. Okay. Now, we can check. Right, I mean, addition is, I guess, easy, right? We can just ask, for example, okay, so what's the, like I can ask you, what's the multiplication of, say, like A times B, right? What would this be?
AB plus.
It would actually be, right?
Yeah.
Okay. It's just the definition. Okay. All right. But we know that that this is a ring. Okay.
So this is exactly the same. I don't remember how did we call it, like the group.
The group we called it quotient group
Quotient
or
Okay.
equivalence class group.
The only difference is the multiplication.
Yeah,
Right?
now you
didn't.
didn't- well,
without having the multiplication.
Yes, but now now the structure of these two will also imply what kind of ring you get, what kind of ring the quotient ring is. Right? Like, is it commutative? Does it have an identity? Is it an integral domain? Is it maybe a principal ideal domain? Okay, like it means something that, like, in groups we always had basically, you know, that there wasn't too much to play with. Like, I think that in groups the only thing that we maybe played with is commutation. Everything else was, right, strict by definition. There was no option to. Okay. All right. So now we're going to state a theorem.
But
It's a single one. Yeah.
the z slash n,
Yeah.
what does that mean exactly? It's modular n? No.
Well, it's not modulo n, but
It's a
You
partition
can-
to classes of.
yeah. It's just like if I took, let's see how to, like, I'll try and just graphically show it, right? So say for, like, I don't know, maybe n equals 3, right? And then I had like 0, 1, 2, 3, 6, 7, and then I had like the negative numbers here, right?
Then you have the three ideals.
Huh?
Then you have the three ideals. Then it's
Well,
equal
no,
to-
actually, you don't have 3 ideals. You have 1 ideal, but you have translations of that ideal, right? So, like, the first ideal would be, right, so n equals 3, so we're looking at 3, yeah. So it would be this, and this, and this, and this, and then this continues to infinity, right? So this would be the ideal,
Yeah.
right? And then the translations, right, so this one would be that. And then you would have that's the first element, that's the 0 element. And then 1 would be equal 1 plus that, so it would be like, I don't know, like, maybe we'll just do it like this, it would be all of these, right? And just so I don't make a mistake. And then 2, right, would be 2 plus 3, 3, so it would be whatever's left that I do.
Mm-hmm.
So yeah, I
Yeah,
mean,
yeah,
it acts like a modulo, right? But,
But I just didn't understand the notation.
okay, so we're good, yeah?
Yeah.
Okay. All right. So let's look at, this is a very simple outcome of something that we did last time. We're going to use a result, so if you don't remember, just have a look at the video that we did last time. So theorem, but it's important. Even though it's very simple, we say that Z quotient group with P, right? With P prime, okay? So P is now prime, is a field. Okay. Now,
With which multiplication?
with the one that's defined by, it's what we defined before. Okay. Multiplication is, again, A times B, right? Which is equal to A plus P times this is the multiplication.
Okay.
Okay. I can get rid of this?
Mm-hmm.
Okay. Okay, so how do we prove it? So I'll remind you, I don't know if you remember, but I'll remind you that we had another theorem that said that, reminder. Okay. We had another theorem that said that every finite integral domain
About 9 minutes.
we've got remaining 9 minutes is a field. Right? Remember this vaguely?
Yeah.
If you don't go to the last session, I think it was, or maybe previous two, we proved this. Okay, so really all we need to do is show that this is an integral domain, right? If this is an integral domain, then that's it. So I'm just going to concentrate on the main, which is a bit partial, but it's the main thing. I'm just going to look at the following. I'm going to say, let's assume that A right times B equals 0, right? Okay. And maybe we'll add also that that's AB, obviously. We know this is all definition, and we'll assume that A times B equals 0, and now we need to show that either A is 0 or B is 0, and if we show it, then it's an integral domain. And actually that's pretty easy because, right, if this is true, then we know that A times B has to equal K times P. K, right, belongs to Z, right? Some integer. So the only way that this will get us in the 0 domain, or actually maybe I'll write it like that. Okay. The only way that this will get us into the 0 coset is if it's a multiple of P, right? Because the 0 coset is actually P. And since P is prime, and we actually, this is where it gets a bit funny, but we never actually defined prime, but prime, the proper definition is that if P is prime and we define that, like, definition of prime is, I think, it's something like this. If P divides AB, then either P divides A or P divides B. B, not D. Okay, so that's the proper definition of prime. And we see that here, what we're claiming is that P divides AB. Okay, so it must divide either A or B, or both, by the way, but who cares? I mean, that's an easy thing. So if that's true, let's, without loss of generality, right, just assume that P divides A, right, and say if P divides A, then obviously A has to equal 0, right, because it's a multiple of P. We're done. We could have done the same with P. All right.
You need to prove also the identity.
Yeah, so I said I'm going to leave that out. Yeah, I mean you would, yeah, like for a complete proof, you to show that it's an integral domain, you need to show like commutative and that it has an identity, right, for multiplication, and maybe we can assume that it's abelian because that's easy. But I'm going to skip all that. I only proved that it's got no zero dividers. We'll leave it at that. Okay. The rest is easy. You can do it yourself. I mean, this is also easy, but maybe more unique. Do we want to continue a little bit? Just to finish the isomorphism? I think it's worth it. It's not going to take more than an extra half an hour. Just so that next time we can move on to finite fields. Okay. So, so actually that's what we're going to do now. So this is, by the way, this is like the first finite field that we've spoken about, right? Just noting. Okay, so let's do a quick preparation and then show the first isomorphism theorem, and I'll try and just give you little reminders of the first time that we did it for groups. For groups, we actually, I think, went through it very thoroughly, and it's exactly the same. So we're just going to skip through it without all the details that we did for groups, and if you need, I suggest go back and view it again, and it'll maybe, make a little bit more sense if it doesn't now. Okay, so we are going to start, you remember, first of all, we need a very special structure for groups. We called it a group map. Okay, so here it's not called a group map, it's called a, actually I would call it a ring map. I haven't seen it, but it's called a ring homomorphism. Okay, so what's a ring homomorphism? It's a special mapping, okay? And we're going to use R2S, okay? Now, both R and S are rings, okay? Okay, maybe it's worth mentioning. Okay, but nothing else. Like I'm at the moment, I'm not asking for anything more that they are just any rings, okay? But what we are going to demand from this mapping for it to be a ring homomorphism is actually two things, which you probably could have guessed. We want it to be homomorphic for addition. and we want it to be homomorphic for multiplication. So that means if you look at the left side says do the addition or multiplication on R and then map. The right side says map and then do the multiplication or addition on S. And you get the same result. Okay? Now, when that happens, and maybe you could do it as a home exercise, this is sufficient to actually preserve structure between these rings. Okay? So whatever structure we had on R, we will have something dual. Okay, I won't say the same, but something dual on S. Okay? This will force it. Okay? And we're going to use it in a second. So if we had an identity in R for multiplication, then we'll have to have an identity in S for multiplication. And it will act in a dual way because it has to obey this. Okay? So a ring homomorphism is a very special type of map, and it's a very restrictive type of map. Okay? And this is the basis, this is what we use for the isomorphism theorem. This is actually, in my opinion, the main point. This is what leads to everything. Okay? What you can see, and we mentioned it previously, is that actually this map doesn't have to be surjective, meaning that S doesn't really need to be completely covered. And we could actually narrow this down. I'm going to erase it and then bring it back, but we could narrow it down to image of phi, right? It would be sufficient for our purpose to just talk about R being mapped into the image of phi, right? The image of phi is a subset of S, okay? And it's the only subset that we're going to be interested in, but we define it over S even if this map is not surjective, and still it works. It just leaves certain elements of S out of the game, right?
Wait, correct me if I'm wrong, it doesn't mean that if you have an identity on R, you also have one in S. Right? Like I can think about having R as the integers, having S as the even integers. So the integers have an identity, the even integers don't have an identity.
But you would have to have something act as an identity. Okay, because otherwise, what would you do when you multiply? Like, how would you get, right? Here, if I have like, if A is the identity, if I substitute A to the identity, right? Then I would get like phi of AB equals phi of B on this side, right? Because the identity. I need to get the same thing here. So whatever A is here, phi of A has to act the same way. So it doesn't matter what it is, it's an identity. Right? An identity is defined as something, identity for multiplication. If I multiply something by it, I get the same element that I started with. Like any element times the identity is itself.
So
that has to be kept. Otherwise, it's not a homomorphism.
Right. So what's confusing me with my example? If phi is just multiplying by 2.
Yeah.
So you get on one side the integers, and like R is the integers, S is the even integers.
Okay.
Okay. So phi of identity times B is phi of B, and on the other side. Okay. So
no, but how do you do here? I'll give you something
so
simple.
this is not
How do you do? It's not, because how do you do? What's phi of 1 times 2? What does it translate
Yeah,
to?
okay. So
Okay,
it's not
so it's not a homomorphism yet.
okay, yeah.
It could do something else with this map. Like I could create a map between all integers to only the even integers that is a homomorphism, but it wouldn't be the normal.
Yeah, you need to change the
Multiplication.
operations.
Yeah, and we'll see it in a sec because that's exactly
Yeah.
like z over 2, right? Could be like that map.
Okay.
Actually, not z over 2. No, that's not correct. But I could think of maybe another map. We'll think about it offline.
Yeah.
Okay.
Can you understand?
It's like the dual of z over 2, right? Because z over 2 folds everything into two things, but here you want to actually take like the dual of it, right? Like half the space.
Like I want to say you don't have a homomorphism. Like you don't have a homomorphism if you keep the usual multiplication on
Yeah,
zero
if
over
you-
two.
Yeah, but like okay, so I'll tell you what
Like, you can find.
I'll tell you what I'm thinking of. Okay, so what if I did something like this? I don't know. I mean, maybe this is wrong, but I think it's not. I don't know. You tell me, okay? Let's say that I had here like I don't know. Let's just look at the positive. Oh, sorry. Right. Just trying to like show an idea, and this would be 0, 2, 4, right? Okay. So what if I mapped like this? Okay.
Okay.
And then I would say that, okay, like I would create these cosets, and then I will just say that the multiplication of these two cosets is the same as here. I don't know, maybe the coset would be always get the value of like the first number. Okay. So then I think this would be a homomorphism. I think. I mean, there may be something wrong here because I just did it now, but I think that you can play with it.
Yeah, you need it.
So like if you have for example, let me like because the last example we discussed was R over P, right?
Yeah.
Then if you want
You mean Z over P?
Z over P. Let's take
Yeah.
Z over P P1 on one side, and then I define a phi that this map goes to some image of phi, which is a subset of some S over P2.
P squared.
No,
What's
not
P2?
P
Oh,
squared.
another P.
Yeah, it's
Like Q. S
yeah.
over P to S over
S over
Q.
Q.
Okay.
So is it allowed from just this point?
Look, it's technically just look. I'll say it again. If you can define a map
Right.
and it obeys these two
So the
things,
R goes to S must be a pre-requirement.
yeah, you create whatever map you want. These two are rings, so I've got addition and multiplication. I've got all the minimal things that I need. So I've got abelian for addition, and I've got closure, associativity, and distribution between plus and mult, and that's it. And if you can define a map that obeys these, and it's homomorphism. That's it. Homomorphism essentially means I can go back and forth.
Why?
I can do it on this side, I can do it on that side. Doesn't matter. Okay. All right. So what we're going to do now, we're going to again do some reuse of what I already wrote. Okay. And we are going to now do the. And again, this is going to be very summarized. Okay. First, Isomorphism Theorem and for rings. Okay. So everything here is rings. I'm not going to even mention it. What do we have? So we've got this phi. and this is a ring homomorphism, okay, what we just defined. Okay. We start with that, and we said again, this preserves the structure. Okay. So whatever structure we had here goes to here. All right. Now, if I have a ring homomorphism, okay, necessarily I can define, right, this exists, right? Why does this exist? Because what's a kernel of phi? It's the map of everything in R that maps to the additive identity of S. Okay? So it doesn't matter even if S, like I don't care about the multiplicative identity. This is important. I only care with the kernel, I only care about the additive identity. And the kernel is all the points in R that map to 0 essentially in S, and we know that 0 exists. So obviously, not obviously, but in a like typical map, you know, with like usual numbers that we like, we would have like at least 0 map to 0, right? And then we may have some others, like if I don't know, if say we map like if this would be like right, like z over p, then it would be 0 and p and 2p and 3p, they would all map to 0, right? Okay. Now I'm going to give you a homework exercise to prove that kernel phi, when I have a ring homomorphism, its kernel is an ideal. It's not hard, okay? But we're not going to show it now. That's for you to do offline. Now we're going to define. So we're given these, okay? We're going to define a projection pi, okay? Projection is also a map. It's just a special kind of map that does the following. It takes the quotient ring of R over kernel of phi, okay? So we take R, we essentially, you know, partition it according to the kernel of phi. Oh, sorry, that's not what I meant. That's not a projection. It's going to do a reverse projection. It's R into R over kernel phi. Okay. So it's basically just taking all the elements in R and dividing them into these cosets, right? It's the actual partition, okay? We call it a projection as well. Right? It's the projection of the elements from R into these cosets. And then what happens, and this is a nice thing, then there exists always a unique isomorphism that we will call, and I'm trying to use, I'm using actually like the same terminology that we used last time, just to keep it simple, from this guy, right? The coset, right, or those like residue classes, right? The quotient group, we've got right, into the image phi, okay? How so? So we can write it. I'm going to draw it out because I think to me it makes more sense. Okay, because we can write it in a short way, but it's more confusing. So what's the isomorphism? And we did this last time. We start with R, right? And we project it onto R over curve phi, okay? And then down here, we have, or maybe we'll put it here, we've got the image of phi, which we know is in S, okay? Maybe it's the whole of S, right, if it's surjective. And then we've got this map, and then we've got this map, okay? And what we're saying, and this is actually, I'm also going to remind you, and you can check in our previous session, this is a composition of three functions. And this is called a commutative diagram, and it means that if we want to go from R to like the image of phi, right? We want to do this guy, right? So we can do it in two ways. We can go directly and just use this ring homomorphism, or we can project it over the curve, and then there exists a unique map. This is a unique map that will map this guy to here, okay? And this map is isomorphic to this, okay? That's what we're saying. Now, this map is isomorphic, okay? Like what we see here and what we see here. Now, I'll remind you that isomorphic, right, is homomorphic with injective. Well, essentially it's isomorphic with bijective, right? We're looking at the image. That's also surjective. That's always surjective, right? But we need it to be injective.
It's homomorphic plus budget.
Yeah. Yeah. Now, homework exercise. I'll send all this by email. I'm just doing it because we're on the video. So I want you to prove this. And I'll give you just the outline, okay, of how to prove it. So basically, I need to show the following. We're going to skip, actually also need to show, there is a sense of showing that phi tilde is well defined, but we'll assume that it's well defined. We need to show that the following things on phi. We need to show that it's homomorphic. Right? We need to show that it's injective. We need to show that it's surjective. And we need to show that it's unique. Okay. And then we're going to assume well defined. You can check what that means, and if we can show all of these, then it's an isomorphism. Now, just quickly, and this will really just take 2 seconds. We're going to show how to use it on our favorite example. Okay, so using the same terminology and just to show why we care, right? Why this is useful. So if we have phi that is z to zp, right? And when we say this, we actually mean that phi of a equals a mod p with the usual modulo, okay? P prime, okay? Then we know that the kernel of phi is p, right? Is that ideal, right? Principal ideal. And then, right, what we can do is the following. We can show that, right, if we take Z and we map it to, or we project it to Z over P, over the kernel, right, then there is an isomorphism from Z over P to ZP. So the quotient ring, or the residue class ring of Z over P, right, acts exactly the same as this modulo guy. Okay, that's isomorphic. Maybe one more comment that could be useful, right? Just to seal it off, because next time I really want to just start with finite fields. So this is not necessarily this is not about isomorphism anymore, but, and I think we did it a little bit, we actually got into that discussion before, but what we can do, so we can use a mapping to transfer a structure from a set with structure to a set without structure, okay? We can force a structure on a set, okay? How do we do this? So if we have R, say, a ring, okay, and S is now just a set, and we've got, say, a bijective map from R to S, okay? Or we define a bijective map from R to S, and we make sure that that map is homomorphic, right? S has got no structure at the moment, but once we do this, right, we just say that phi of, say, R1, right, plus R2, right, equals, I'm just going to, we're going to assume that like phi of R1 is S1, okay, just so that this is S2, right? If we force this structure, and this is bijective, okay, so this is just like all, we build this, we construct this. Right, then we essentially created an isomorphism between R and S. Right? So now whatever applies to R works on S. Okay, and this could be useful. It would mean that, right, it would mean that this plus and this multiplication could be defined arbitrarily, right? They could be like maybe just defined by a table, okay? They don't like, but it just says that we can really take any set that we want if we want to take a structure that we want, that we like, we want to transfer it to a set without structure. We could always engineer these operations to a way that we get the same structure. Okay? And this is all we need to do. We just need to make sure that the mapping is bijective and homomorphic. Okay? So that could be a useful tool. Okay, we're going to stop here. Yeah.
Thank you very much.